We often think of the birth of the universe as pretty much the same all over the place. Our solar system is just one example of how stars form from collapsing clouds of dust and gas. But what if there are other ways to make stars? What if some parts of the universe didn't have enough of the right stuff for this to happen at all? What would a starless galaxy look like? It turns out that our universe went through such a phase, and it was a lot longer than you might expect. It's called the Dark Ages, and it lasted tens of millions of years. But don't worry, we're going to light up this era of the cosmos with some science. Stars weren't always shining in the night sky. For the first few 100,000 years after the Big Bang, the universe was filled with a murky fog that blocked visible light from traveling more than a few feet. This period, which astronomers call the Dark Ages, came before the first luminous objects formed and the cosmic web of galaxies began to emerge. But how could this be? Stars are born when massive clouds of gas and dust collapse under their own gravity. As the material condenses, it heats up and forms an embryonic star surrounded by a swirling disk of leftover matter. As the star gets bigger, its intense energy blasts away the remaining gas, leaving behind only a hot plasma. That's how the sun formed, and so did all the stars in the Milky Way, or so we thought. In 2021, astronomers reported evidence for a different way to forge stars, one that doesn't require any gas or dust, but instead relies on the shock waves generated by exploding supernovas. These explosions are so powerful that they can ionize nearby hydrogen atoms. When these hydrogen atoms absorb ultraviolet radiation from the supernova, they get excited and release huge amounts of energy in the form of light. And where there's light, there are photons. When these newly created photons interact with other particles of matter, they bump into electrons and knock them into higher energy states. Then, when the electrons fall back down to their normal energy level, they release even more photons. And this generates a cascade of photon-electron interactions that spreads through the gas cloud. Eventually, the entire nebula is filled with free electrons and ionized gas. The cloud becomes transparent, and what was once a starless void becomes a stellar nursery. Gravity causes the ionized gas to clump together and collapse. Once the clumps become dense enough, they begin fusing hydrogen into helium and become new stars. So does that mean that the early universe didn't really have a dark ages after all? Well, not exactly. While this process can explain how some galaxies formed early on, it's still believed that most of the stars in the observable universe formed after the Dark Ages ended. So we know there were certainly periods of time and places where stars weren't shining, but a total absence of stars across the whole of the cosmos? No way. After the Big Bang, the universe had a lot of things you need to make stars, lots of hydrogen. And helium, plus some heavier elements forged in the cores of the first stars. In fact, the conditions were so perfect for star formation that most of the universe's stars formed within the first few billion years. But there was still a fair amount of time, about 200 million years, before the skies were filled with stars. What kept the cosmos dark? One idea is that the stuff between the galaxies was to spread out. Even though the early universe was very dense overall, most of the matter was evenly distributed. And while there were certainly regions with slightly higher densities, they were still pretty far apart. The distances between these clumps of matter were larger than the size of the clumps themselves. And the reason why this mattered is because the average spacing between atoms in a typical molecular cloud is about 1 trillion times smaller than the spacing between those clouds. If you've ever watched smoke rise from a candle flame, you've seen this effect in action. When the smoke condenses, it forms tiny solid particles suspended in a gas. This is why smoke looks dark. But if you increase the flow of air, those solid particles never condense and the smoke appears lighter. This is because the increased flow of air keeps the particles in the gas state, meaning there's nothing for light to scatter off of. The same thing happened throughout the early universe. Regions of space with low densities of matter didn't have enough particles for light to scatter off of, so the fog remained thin. But if those regions had been denser, the photons and the cosmic microwave background radiation would have bounced off the extra particles and turned the fog thick enough to block starlight. Those regions would have remained dark until more matter condensed within them, either by further gravitational collapse or through collisions with other clouds of matter. So the Dark Ages were probably a lot longer in regions of space that were less dense. But why didn't those lower density regions eventually collide with the higher density ones? You see, it's not quite as simple as bumping into each other. Even though the early universe was filled with matter, it was also filled with radiation. All that radiation was moving very fast, like up to 300,000 kilometers per second. So if two clouds of matter did get close enough to each other, the radiation pressure from the photons would push them apart before they could merge. Only when the clouds slowed down below a certain critical speed could they start to collapse. But at this stage, the clouds had cooled to the point where the gas within them could no longer support itself against gravity and collapsed. And by then, though, the cosmic microwave background was no longer the dominant radiation in the universe, and the clouds had stopped feeling the effects of its pressure. They had finally reached a time and place where they could combine. But if these clouds were so evenly distributed, how do we know they existed in the first place? Astronomers found their signature in the cosmic microwave background. Some regions of the sky are slightly warmer than others. These are the places where the matter was more dense, creating a thicker fog and preventing light from reaching that region as easily. Since these areas were effectively cut off from the rest of the universe, they took longer to cool down. And that's not the only evidence we have for this Dark Ages period. Without telescopes, we can't actually see more than a tiny fraction of the space around us. So astronomers use computer simulations to reconstruct models of the early universe and compare those models to observations. So far, the best model matched the real universe, which means that the Dark Ages must have been real. Some scientists even think that this period lasted even longer than the 200 million years we've settled on. But the jury's still out on that one. As for what caused the end of the Dark Ages, it's likely that the collapse of even just one cloud of matter kicked off a chain reaction. Once the first stars started to form, they produced heavier elements in their cores, like carbon, oxygen, and neon. As these stars exploded, they expelled these elements into space, and the next generation of stars incorporated them into their atmospheres. Some of these new stars became giant balls of burning helium. Others were large enough to fuse helium into carbon, oxygen, and neon, and some were even big enough to start fusing carbon into heavier elements. These heavy elements blocked the hydrogen in their atmospheres from collapsing inward. As a result, the next generation of stars was much more massive and shone much brighter than the first. In other words, the universe went from having almost no stars to having lots of dim stars to having lots of bright stars. And with that, the Dark Ages came to an end. Today, the sky shines bright with more than 100 billion stars in our galaxy alone. Every year they create a dazzling display of light shows, which we can enjoy thanks to the light pollution they produce. And who knows, maybe one of those stars will someday become the center of a new dark age, but it won't be anytime soon. Thanks for watching this C-Show video.